Okay, so we're going to take a look at an application of the dot product here called an orthogonal projection. Okay, so an orthogonal projection, what you see here is just two instances of a drawing of what an orthogonal projection is. So we have two vectors, u and v, and theta we see is the angle between them. All right, we have the red vector u, the blue vector v, right? And in the black, down here we have another vector, and we're going to call this vector the projection. Oops. So I'm going to introduce this notation. Oops. All right. So the way you read that is the projection of u onto v. Right. So if you look at that dashed dotted line from u to v, the angle that makes is a right angle. Right. So here, this angle here, and then this angle here, if it wasn't clear, right angle. Right. So almost you can think of if we have a flashlight right above u, and almost like the shadow that it would u make onto v, right? So you can think of that as the projection. So you want to kind of derive a formula to calculate that vector, right? Now keep in mind here, when we're referring to this is referring to the vector. All right, and it is a vector that is parallel to v. Okay, now and again, what's special about that is really it's aimed to say, all right, the vector, the part of u that is in the direction of v. All right, so let's start kind of deriving a formula by first finding what the scalar projection is. All right, now the scalar is exactly what it sounds like. It's not a vector. So we're going to look at another thing, the scalar projection of u onto v. Okay. All right. So that is a scalar, right? In other words, what it is referring to is the signed magnitude of u in the direction of v. All right. In other words, if we think of the vector to be the shadow, the scalar projection would be the length of that shadow. All right. Again, another way to think of it is how much of u is in the direction of v. Okay, so let's take a look. Let's try to figure that out first. So the scalar projection, excuse me. I'm going to define as the component of u okay. All right, so we're going to define this part here. Okay. All right. So if we take a look at, let me draw our situation here. U. Right, if this is V, this is theta. All right, so we could see here we have Sorry. Okay, so we can see here that looking at this, we could see that the component well, excuse me. So let's look at the dot product, right? U dot V. Right, so the dot product, if we look at in terms of the magnitudes of the vectors, is the magnitude of U times the magnitude of V times the cosine of the angle between them. All right. Okay. Now, if I rearrange things here, let me write it instead like this. Theta. All right, now keep in mind all of these quantities here are scalars, right? The magnitude of U, magnitude of V, U dot V, those are our scalars. And I'm going to look at the right triangle here, where the length of this hypotenuse is the magnitude of U. We have the angle theta. All right, and let's figure out, well, what is this quantity here? All right, let's call this quantity x. All right, actually, here, yeah. Excuse me, we already have a name for it. The scalar component, the scalar projection component, the scalar projection of U onto V. Okay. All right, and just kind of here, doing some basic algebra here, we could see that the cosine of theta is equal to the magnitude of U, excuse me, got that reversed, the component of U in the direction of V over the magnitude of U, the hypotenuse. Adjacent over hypotenuse, and then solving for the component, we could see, all right, the component of U in the direction of V is equal to cosine theta U in the direction of V is magnitude of U cosine theta. All right, which I see right here. All right, so we could see, so we're going to swap that out, and we see, okay, so the dot product of U dot V is equal to the magnitude of V times the component of U in the direction of V. All right, okay. And then solving for the component of U in the direction of V, I now have a formula that I can use. All right. Okay. Oh my goodness. Okay. All right. So there we have to find the scalar component or the scalar projection of U onto V. Right? In other words, the sign magnitude. How much of U is in the direction of V, and this quantity tells me how much that is. Okay, so that gives me the quantity, but how can I determine from this, or using this, I would like to find the actual vector. Right, so I would like to find the projection of U onto V. Right, in other words, looking at our drawing here, the actual vector here. Right, how can I find that vector? Okay, now one thing to notice is that it is parallel to the vector V, right? And I can think of it, well, if it is a part of U, I want to say, all right, how much of it in U, right? So the way that I can think of this projection would be, all right, the amount of u, in other words, the length of the shadow. Right? And again, what do we need for a vector? It needs a magnitude and a direction, right? Well, what direction is it in? Well, if it's parallel to v, it has to be in the direction of v. Now here we have to be a little careful here, right? It should be in terms of, remember, if we're going to add a we're going to introduce a quantity here, we want to make sure to kind of normalize this, right? To make this into a unit vector, right? So that way I know it's in that same direction, and the amount of it is only the amount that I calculate with the in terms of u. All right. So keep in mind here that this quantity here is the component onto v. All right. So I'm building essentially the vector, right? The direction in terms of v, but again, make sure that you make it a unit vector so that you capture only u, or the part of u that is going in the direction of v. All right, and then here, doing a little simplification here, we have the norm of v squared times the vector v of v. Okay, and again, notice that these quantities here, right, keep in mind that's just a scalar, right, some real value number, and then v is a vector, right? So we could see that this calculation makes sense. I have a scalar multiplication of the vector v. Okay, all right, and again, you can also, another formulation of this, you can think of this as u dot v. Right, the norm squared, right, or the magnitude of a vector squared is the same as the dot product v dotted with v. Okay, so let's try an example here. Find the scalar projection. Right, so find the scalar projection and vector projection of the vector u equals to 1, 1, 2 onto the vector v, which is equal to -2, 3. Okay. All right, so let's start with the scalar projection, right? The component of u onto v. So that's going to be u dotted with v over the norm of v. Okay, so let's do these separately here. What is u dotted with v? And that is 1 times -2 plus 1 times 3 plus 2 times 1. So that gives me a 3. All right, and then the norm of v, the magnitude of v, is square root of -2 squared plus 3 squared plus 1. So we get square root of 14. All right. Okay, so leading up to the scalar projection, we get 3 over root 14. All right, and again, the way you think of that is the amount of vector u that is in the direction of v. All right, so now let's actually look at what that vector looks like. Okay, the vector itself is the projection u onto v. And then using our formula, we have u dotted with v over the norm of v squared times the vector v. All right, and this is going to be 3/14, right? Magnitude of v squared. And then the vector is, what was v again? -2, 3, 1. Okay. All right. Now, let me show you a picture of this. So this. All right. Okay, so if you see here, all right, we have the vector u and the vector v. Right, you have the dotted line. It kind of drops straight down onto the vector v. And then, let me zoom in here. And then what you see there in red is that vector p, right, the projection, right? Notice that it is parallel to the vector v. All right, and you can see that that dashed line is dropping directly down and it's meeting the tip of that vector p. All right, so that calculation, right, again, it's telling us, imagine there was a kind of a flashlight right above you, all right? And then it's shining down, and the length of the shadow would be that would be the scalar projection that we found, right? And the shadow itself would be the vector, that vector p. All right, thank you. That concludes this section.